in
I
this
want the
process.
raw footage, not the YouTube version.
I'm not sure whether that exists on any physical machines here or whether it's all
It's
somewhere.
in the cloud, somewhere in the cloud.
Otherwise, Pascal is just here, we can ask.
Okay, so I think we should start. If you remember from Alessio's talk, he mentioned Kakara, which he used to elaborate proofs. And he, sorry?
Never heard of it.
Never heard about exactly. And he basically said a sentence like, I don't want to talk about it or explain how it works into details, which is very good. Now we have Bruno who will explain you in great details how all of this works. Bruno, the floor is yours.
Okay, so hello everyone. So thank you, Matthias, for the introduction, and thank you for inviting me to give this talk as well. So as you said, my name is Bruno. I'm a master's student at UFMG in Brazil, and I'm going to talk to you guys about Karkara, which is a proof checker, an elaborator, and in the future also a translator for Aleth. So I'm sure most of you are familiar with SMT solvers and SMT proofs and all that, but it doesn't hurt to refresh your memories. So SMT solvers, they are very crucial tools in many applications like proof assistance, program verification, and all that. But they are also very big and complicated tools, and their code bases are very hard to make sure that it's working. So oftentimes you can find bugs that affect the correctness of the results in SMT solvers. So how can we trust that these tools are correct? Well, one way of doing this is using what we call SMT proofs. So we can instrument the solver to produce a proof. And in this case, we're really worried about the unsatisfiability case. So then the proof is going to be a certificate that the formula is actually unsatisfiable. So it's going to formally justify the reasoning that the solver took. And these proofs can be checked independently from the solver, which means that we are able to trust the results of the solver without having to actually trust the implementation of the solver, which is very useful. And in practice, checking is much simpler and quicker to do than actually solving the problem. So in particular, we are concerned with the Aleth format, as you probably know. So Aleth is a pretty well-established SMT proof format. And currently it is supported by both Verity and CBC5 SMT solvers, along with some other tools, if I recall correctly. And Aleth has a syntax which is very similar to SMT-lib, which is the standard input language for SMT solvers. And also Aleth is a very flexible format. So this means that solvers can produce proofs with varying levels of granularity. So for example, you can have a solver which produces a very coarse-grained proof, which is easier to produce, but can be harder to check. So it's kind of relying on a powerful proof checker. Or on the other hand, you can have a solver which kind of takes the effort to produce a more fine-grained proof, which is probably going to be harder to produce, but it's going to be much easier to check. So here we have an example of an SMT-lib problem and an Aleth proof for it. So things of note is that the general structure of the proof starts with assume commands. So the assume commands kind of relate to the assertions of the original problem, and they introduce the premises of the proof. Then we have a series of steps. So each step is going to conclude a clause, and each step is also going to have a rule associated to it. So the rule is kind of like the logic that the step used to reach that conclusion. And steps may also have premises, which can be other steps or the assume commands or something like that. And at the end, you're going to have a step, which in this case is T5, which reaches the empty clause. And as we all know, the empty clause is a contradiction. So this proof as a whole is showing that from these assumptions, we can reach a contradiction. So the formula as a whole is unsatisfiable. So how might we go about checking these proofs? So one way that has historically been done is by reconstructing the proof in a proof assistant. The way that this is done is by translating the language of Aleth into the language of the proof assistant and then asking the proof assistant if everything is correct. And this is very interesting because it allows a lot of trust in the correctness of the checker, right? Because it's very unlikely that the proof assistant is going to have a bug because it relies on a trusted kernel. But it does have some drawbacks. So for one, proof assistants usually are very slow because they are complicated tools, so they don't have great performance. And also the usability is not great. It's not nice having to spin up a whole proof assistant every time you want to check a proof. Another issue is that sometimes, since proofs can be very coarse-grained, you might have a proof that's very hard or very slow to check, and that can result in reconstruction failures. So maybe you have a proof that just takes a very long time to check in the proof assistant and it times out. Or maybe you have some complicated step that the proof assistant doesn't have support for checking, so it also fails in that way. So instead of doing that, one might prefer to have a standalone checker. So a checker that was created with the sole purpose of checking ELETH proofs and reads them directly. And as you might guess, that is exactly what Karkara is. So Karkara is this tool we developed here at UFMG, and it is an efficient and independent checker for ELETH proofs. It was developed in Rust with a focus on efficiency and also usability. It was also named after a bird, so the ELETH format is named after birds as well, so we kind of followed the theme there. And Karkara is named after Carcara, which is this beautiful bird native to South America. And being a standalone checker, and especially being not a certified checker, Karkara doesn't afford the same level of trust you have when you're reconstructing the proof in a proof assistant. But it is much faster, it is easier to use. So in some applications, it might make sense to use it. So let's talk a little bit about how Karkara can check a proof. So let's start. Okay, so for each step in an ELETH proof has a different rule, and the way we check that step is going to depend on that rule. So since ELETH has currently over 100 rules, we had to implement a checking procedure for each of those 100 rules. And as we'll see, the flexibility of the format means that some steps can be very tricky to check, and just some general properties of the proof can be very annoying. So let's start with the assume commands, right? So like we said, an assume command introduces a premise of the proof, and it, in theory, should relate to an assertion in the original problem. So when Karkara is parsing the problem, it's going to collect all of these assumptions in a hash set. So in general, when it's going to encounter an assume command, checking is basically just accessing that set and seeing if the term is there, which is very easy, right? So far, so good. The problem is that one of the properties of the ELETH format is that the solver is allowed to implicitly reorder equalities when it's producing a proof. So here in the right, we have an example of this. So this is an SMT-lib problem that has the assertion that B is not equal to A. And then in the ELETH proof, the solver decided to change this assertion into A is not equal to B. And of course, semantically, these two terms are obviously the same, but they are not syntactically equal. So the checking procedure we mentioned earlier is not going to work for this. So when we encounter an assume command like this, Karkara must then iterate through all of the premises in the problem and compare them to the assumed term, modulo this reordering of equalities. So this comparison, we call it a poly-equal check. And it can be quite slow, especially because it has to traverse the terms maybe up to their depth. And since we have enormous proofs, you can have very deep terms. So this can be genuinely a bottleneck in the performance of checking a proof. And especially because this doesn't happen only on assume commands. This can happen in pretty much every rule of the proof. So as some examples here, we have the REFL rule that models reflexivity, and we have like the flip equality, congruence rules, instantiation of quantifiers can also have this issue. So in general, in Karkara, we have to deal with this poly-equality check in almost every rule. Right. So another notable rule is the resolution rule. So it's heavily used in SMT proofs because it models the propositional reasoning of set solvers. And in ELETH, the resolution rule looks like this. So it can take a series of premises. So it really is like a resolution chain. And the conclusion is going to be reached by resolving each of these chains, each of these binary resolution steps one by one. And in this case, P1, P2, and P3, which are given as arguments to the rule, are the pivots of the resolution step, right? The problem is that in general, these pivots are not provided in the proof. So the checker then has to infer which pivot was used for each of these binary resolutions. So to do this, in Karkara, we use a greedy algorithm that's going to look at the conclusion clause of the proof, and it's going to guess which of the pivots, which of the terms are pivots based on which terms appear in the conclusion. So here's an example of how this works. So let's say we have this resolution step and we don't know the pivots. If you look at the first two clauses that we're going to resolve, we can see that they both have the A literal with different polarities in each clause, but the A literal does not appear in the final conclusion of the step. So it's reasonable for us to assume that A is then the pivot for these two clauses, right? So we're going to mark A as the pivot. And then we resolve these two clauses using A as the pivot and continue on. So if we look at the next clause, you see that it has the C literal, which does not appear in the end conclusion. So we're also going to assume that C is also a pivot, and we continue this until we reach the end of the step. And in this case, everything works, right? So we're able to successfully check this resolution step by inferring these pivots. However, this algorithm is not complete. So there are some valid resolution steps that will be rejected by this algorithm. So as a fallback, Karkara also has to implement an algorithm which is based on reverse unit propagation, which is more complex and also slower, but it is in fact complete. And kind of the takeaway here is that if the pivots were provided in the first place, everything would be easy, right? So checking would be easy, fast, complete, everything would be fine. Which brings us to elaboration, right? So besides just checking a proof, Karkara can also do what is called proof elaboration. And by elaboration, we mean taking an LF proof, which may have very coarse-grained steps, very hard-to-check steps, and kind of breaking it down into finer-grained steps, producing at the end a proof that is hopefully easier to check. And so, like I said, besides checking, Karkara is also able to do this. So let's take a look at some of the key elaboration procedures that Karkara can do. Right, by the way, it doesn't really make sense to elaborate a proof with Karkara if you just want to check it with Karkara again, right? Because you can just check it in the first place and it's going to work. However, if you are using Karkara as kind of like a middleman between an SMT solver and a different tool, then it might make sense to elaborate. So for instance, if you want to reconstruct a proof in a proof assistant, but these coarse-grained steps mean that checking is very slow, you might use Karkara as a middleman to elaborate the proof and produce a proof that is easier for the proof assistant, so you can then check it. And since proof assistants in general are much slower than Karkara, even when Karkara is elaborating, it might make sense performance-wise to do this elaboration. If you want to translate the proof to a different format, also it makes a lot of sense to elaborate it beforehand, because then you have to deal with less of this horrible, weird stuff that can happen in proofs. So, okay, so let's come back to the issue of the implicit reordering of equalities. So, like I said, LF can allow solvers to implicitly reorder equalities when they are producing a proof. And that is very complicated and makes checking really annoying. So we implemented a procedure in Karkara to completely eliminate this implicit transformation. So let's go back to that example I gave of the assume step that had this implicit reordering. So this would be much easier to check if the assume H2 was instead assume H2 B does not equal A, right? So it matched exactly the assertion in the original problem. However, we can't just change the term of the assume because the following step, T3, uses that assume as a premise. So if you just change the term, it's going to break the resolution. So instead, we also have to add some intermediate steps that from the quote-unquote fixed term reconstruct the original term, so then that every step further down in the proof that uses that is still going to work. So this is like the correct way to elaborate that proof. So notice that we changed the conclusion term for H2. So now it does match exactly the assertion in the original problem. But we also had to add this extra step here, H2.T1, which uses the not sim rule to kind of flip back the equality so we get the original term. And then the resolution step, now instead of referring to H2, it refers to this new step we added. And in this case, it was pretty simple to do this. We only had to add one step. But for bigger terms, you might have to add like a very large number of steps. So in general, this can make the proof grow quite a bit. So like I said, this implicit reordering doesn't happen only on assume commands. It can happen on pretty much all rules. So we had to implement a similar procedure for all of the rules that can be affected by this. And we reached a point where now if you elaborate a proof with Karkara, you can be certain that there aren't going to be any implicit reordering of equalities in the resulting proof. So it is much easier to reconstruct it or translate it or whatever you do with it. So another interesting elaboration that we can do with Karkara is elaborating reordering steps. So the reordering rule takes a single clause and it's going to produce a permutation of that clause. And this rule is not particularly difficult to check in Karkara. It's quite simple, actually. But it can be challenging to formalize this rule in some other formal languages or to translate it to a different language or formalize it in proof assistants. So to help in that, we also implemented an elaboration procedure in Karkara that can remove all of these reordering steps from a proof. And it's actually quite surprising that we can remove all of them, right? So the general idea is that we remove the reordering steps and replace them with our premise. But then, of course, this is going to affect steps further down in the proof that use those modified steps as premises. So we're going to have to recompute those steps, which is not clear how we can do that. And then we're going to have like another modified step. So we're going to have to recompute steps that use those as the premises, and we're going to have to propagate these changes down the proof until we reach the end of the proof. So, how can we recompute like any step that uses a reordering premise, right? How does that work? Well, this only works because in LF we have this interesting property that there are a very small number of rules that actually accept premises with more than one term. So for most rules in LF, the premise clauses can only have one term. And the only exceptions really are weakening, contraction, and resolution. So we really only need to implement this recomputation for these three rules. So let's see an example here with the resolution rule. So we have this resolution step that uses a reordering step as its premise. So what we're going to do is want to destroy this reordering step, want to kill it, right? But if we do that, then the resolution step is kind of wrong because the order of the conclusion doesn't really match the order of the premises, right? So we would expect that the order of the conclusion of the step is A, C, D to match the order of the first premise. So what we do, well, we have to recompute this resolution step, and we do that just by actually resolving the premises. And now we have a new resolution step that is also modified. So we also have to kind of propagate these changes down the proof. But the key idea is that the only difference is the order of the clause. So again, the only change we're going to have to make is to those three rules: resolution, weakening, and contraction. So there are a bunch of other elaboration procedures that we do in Karkaras. I'm not going to go into detail into all of them because it would take too long. But one thing we do is simplifying some transitivity steps. So there are some steps which can take quadratic time to check. And after elaboration, they take only linear time. We can find the resolution pivots, right? So like I said, we have to infer the pivot sometimes to check the resolution step. So, why not just add those pivots to the proof when we're elaborating, right? So we do that as well. We also do this thing which is called resolution uncrowding. So normally in LF, resolution steps, they can have the implicit reordering of clauses, and they can also have the implicit removal of duplicate literals. And this is also like another thing which is very annoying to formalize or to translate and whatever. So with this uncrowding step, we basically make those transformations explicit. So for instance, for the implicit reordering of clauses, we're going to add an explicit reordering step inside the resolution chain, which will then be removed, of course, because we remove reordering steps. Right. And another interesting thing we can do with the elaborator is we can call external tools to kind of break up hard to check steps. So kind of as an example, what Karkara can do right now, there's this rule called Lia generic, which is very hard to check. It's very annoying. So what Karkara can do is it can call an external solver. In this case, it uses the CBC5 SMT solver. And it passes that step as an SMT-lib problem. So the solver is going to solve it. It's going to produce a proof in LF. And then Karkara is going to insert that proof in place of the original step. So for now, in Karkara, we only really have this as an example. But in general, you can use any external tool to solve any rule, as long as the tool can read SMT-lib and produce an LF proof, which is really cool. Right. So that was kind of the current state of Karkara and its main capabilities. So let's talk a little bit about the things that we are working on and we will work on in the future. So I think the main thing, which you probably have heard in Alessio's talk, I wasn't able to watch the talk, but I'm sure he talked about this, is proof translation. So we are working on adding support directly in Karkara for translating LF proofs into different formats. So namely lambda pi, which is the work that Alessio has been doing, and also Unoia, which is this new proof format for SMT solvers. And this work is actually very exciting because it's going to help integrate SMT solvers and SMT proofs into many more tools and just kind of help connect things. And of course, like I showed, elaborating the proof beforehand can make this a lot easier. Not that it is easy in any way, still is a very challenging task, but elaboration is crucial to make this easier. And a bunch of other things. So we're also expanding support for new theories. So we're adding support for the bit factors theories, strings, data types, and a bunch of other reasonings that SMT solvers can do. We are working on something called proof compression, which is the idea of combining steps and removing steps from a proof to make it smaller. There's also proof slicing, which is extracting a specific step along with its premises from a very large proof. So this is particularly useful for debugging purposes. So if you're developing a tool that produces LF proofs, and something goes wrong, like you produce an incorrect proof, it is very helpful to be able to extract exactly the step that failed and the premises so you can get a better idea of what's going on. Yeah. So, to wrap up, Karkara is currently used by developers of both SMT solvers and some other tools who want to add support for the OLED format to their tool, which is really cool. And Karkara really helps in debugging and helps in this process in general. It has also served as kind of testing grounds for the format as a whole. Karkara has even uncovered some inconsistencies that existed in the format that have now since been fixed. And in general, especially with this more recent work, Karkara is becoming much more than just a proof checker or a proof elaborator, and is really becoming kind of like a multi-purpose, all-in-one tool to work with OLED proofs. So yeah, I wanted to thank all the people who work on Karkara or who have worked on Karkara, whose names are on the screen right now, and thank you for listening.
Okay, I start with a question.
Yeah.
Bruno, you mentioned renaming the proof steps. Why don't you insert them in kind of your other TMP version and then you keep the names?
Right. So we can do that. So you mean for like the assume elaboration, right?
Yes.
So
yes.
yeah, we can do that. So the name is kind of arbitrary. I actually don't remember if currently when we
But I
elaborate.
mean is what you're doing here is you are introducing this h2.t1.
Yeah.
And h2.t1 is replacing h2, which means that you have to rename all occurrences of h2 in the rest of the proof.
Yeah. So the way that Karkara represents proofs internally, the premise is just an index or a pointer into the step. So if we can, so we just have to rename the step, and when it's printing, it's gonna find the right name. So this is not like a problem of like having to go through all the steps that use this. And it's really just a stylistic choice. So we could very well just make assume h2 be like assume h2.h1 or something, and then step h2 be that, but it doesn't make too much of a difference.
Okay, thanks. Yes, Pascal.
Yeah. A question about resolution. So you said that resolution was difficult to check. I guess, I mean, because in Verity, when we introduced that resolution rule, it was clear in my mind that at least the clauses would be in order, right? And if the clauses are in order, it's really not difficult to find out the pivots. I guess that's the reason why you need those reversed unit propagation way to replace the resolution is because in CVC they don't respect the order. Is that right?
Yes. Yeah, you're absolutely correct. So Verity proofs, this always works. The greedy algorithm always works for Verity. But as soon as we get proofs from different solvers like CVC5, it might be the case that this doesn't always work. So we have to have the more general solution.
This is an interesting point, right? Because when we wrote this ALIT format, or when Hansi worked on that, we never thought that this resolution rule would be used with clauses in the wrong order. And so it's kind of a misspecification that, or lacking of specification that has been abused, and then it makes things difficult for everybody, right?
So I think the issue is not necessarily just the order of the clauses. So it might also be the case if, for instance, like, so if the first two clauses here, if the second clause had also like a not B, it might be the case that B is the pivot. And if it could be the case that like A and not A are going to be in the clause, but then they're going to be removed by like something further on. So just looking at the...
You have the valid clause, and then you can just remove everything.
Yeah, you can just remove the whole step, of course.
But in most calculi, clauses are either sets or multi-sets of literals.
Yeah.
And in your case, where you don't have variables, isn't it easy to just always order the clauses using some random total ordering?
That's true.
Yeah, so question. So I think in Karkara and that in general, the clauses are treated as sets. because you have the implicit removal of duplicates and stuff like that. So I'm not sure.
This comes from the SAT semantic. So for the SAT solver, the clause is a set.
Yeah.
So it's the clauses are multi-sets, so a clause can appear several times, but each clause is a set, and we implicitly remove duplicates. There is no factoring movement set.
And so each clause has a canonical form.
Yes.
Yeah, and also the equalities or other things that are symmetric.
Yeah, if you have variables, this gets hairy, but if you don't have variables, it's easy. And SMT.
Problem with equality is when you instantiate them, though, it's not clear how to, I mean, you have a for all x equal y, then it's not clear that you have an order which will be compatible with instantiation.
Right.
Okay. This is the tricky part.
That's the tricky part,
But,
yes, indeed.
I'm not convinced it's possible, but might be.
Oh, it's possible, it's just NP hard.
Okay, yeah, okay. Yes. But, yeah, I mean, for every proof you will manage to find an order.
So you can try any order of literals and then normalize the variables and then compare all the variants which one is smallest in your lexicographic ordering. And pick that one as the canonical form. That works. I do that in E for learning, but I also have a flag that says, if you've tried for long enough, give it up. It's not NP hard, it's exponential. The naive approach is exponential. And of course, you can use better implementations, but I haven't found much better ones.
Any more comment? Otherwise, thank you very much for the talk. And thank you very much for the tool, which is a very useful one.
Thank you, guys.
So, and now we have another reconstruction talk, but this time, so another talk about reconstruction in an interactive theorem prover. But this time it's not lambda pi. Okay, I had Deducti in mind. So Hannah, can you share screen? She's frozen. Probably Zoom crashed. So this time it's about when she would join again. It's about reconstruction, about CVC5 proofs in Isabel.
Hi, sorry I dropped out because Zoom doesn't like it when I share my screen.
Yes,
let me try again.
I think we're supposed to stop the recording. I started.
yeah, sorry.
Wonderful.